Hey everybody. Today what we're going to do is we're going to go through something called Cramer's rule, which we can use to help solve a system of linear equations. So in high school you probably picked up normal substitution and elimination to solve pretty simple linear equations, systems of linear equations. But for you've probably picked up how to use Gaussian elimination to find a row echelon form to find a solution, or Gauss-Jordan elimination to find reduced row echelon form. Today we're going to go through something different that involves the determinants of matrices. So what I'm going to do first is I'm going to walk us through the process to use Cramer's rule and then work through an example afterwards. So when given a system of linear equations, we can write it in ax equals b form. So that would be your coefficients times the variables multiplied by the column matrix or a vector of the variables inside the system which is equal to some numbers. So which is also a list of single numbers, which would be a column matrix or another vector. So the next step after that is to take the determinant of coefficient matrix A, and then we're going to put that aside, and then you're going to swap each column in A with the numbers in B one at a time. So what we would have, let's say we had A, which is, let's make it 3 by 3, times the variable vector, we have x1 all the way to xn, would equal to b1, b2, b3. They can be any number. It's whatever. If you had x plus y plus z is equal to 3, we would have 1, 1, 1 in our A. We would have x, y, and z in our variable, in our unknown vector, and we would have 3 in our right side of our equation. So we would take the determinant of this matrix and then set that number that would evaluate to a number. If the matrix is invertible, never mind. Hopefully the determinant exists, and then you're going to swap each column in A with the numbers in B one at a time. So you're going to take B1, or B1, B2, and B3, plug them in here to replace those numbers in A, and then take the determinant. You're gonna plug B1, B2, B3 in a second time, and then take the determinant again, and then take the determinant after you put B1, B2, B3 in every single column in A. So we can notice that this can be quite time consuming and that is not as useful as using a row echelon form, for example. But sometimes you can be asked to use Cramer's rule specifically. So once you have those determinants, you would have the determinant of the original. You would have the determinant of the one where you put B1, B2, B3 there. You have the determinant of the one with B1, B2, B3 in the middle, and then you'd also have you'd also have the one with B1, B2, B3 on the right. So this is 4 determinants to calculate 3 variables probably. So to find the actual values of the variables let's say for the first variable, you would take the determinant, you would take this determinant divided by the determinant of the original. Let's call this A1. And then you do that for each of the remaining new matrices you created. So obviously we can see that this isn't the best method, and we're gonna keep elaborating on that. And this can probably be more clear once we go through an example. So why might Cramer's rule be useless to some people? We can use row echelon form and reduce row echelon form, and that works every time and is usually faster. And also the matrix, the determinant might not exist. So, and then you would be dividing by 0. So if your determinant of the original was 0, you would have to divide each of the new determinants you find by 0, which would be an undefined value. When can it be useful? If you notice that if I try to use row echelon form, that's going to give me a ton of fractions, and you're not good at fractions, and the test is no calculator, then you might consider doing Cramer's rule by yourself. But usually you would go back to the tried and tested row echelon form. So let's work through an example of Cramer's rule to make it more clear and hopefully make it stick. So our job now is to find x, y, and z. Solve this linear equation using Cramer's rule. So our first step is going to be to rewrite this system of linear equations in matrix form. So we're going to take the determinants, not the determinants. We're going to take the coefficients, of from the left side of the system. So we're going to start off with x, because we know x, y, z. So notice how there's 0 x's in the first one. There's -3y and -5z. The second equation has 2 x's and -3 y's and 0 z's. And then our third equation, we have the 0 x's, -3 y's, and -2z. Oh, we're not going to put the z there, sorry. So this is our a, when we're writing this in a x equals b form. So our variable vector, or column matrix if you prefer, will be x, y, and z, which will be our 3 unknowns. And now if we performed matrix multiplication, we would get a product of the stuff on the right. We have -2, -1, and 1. So, okay, so let's see if we can fit this all on one screen. So we're going to take the determinant of the matrix here. So we're going to, let's do that first. So the determinant of A is equal to, actually we're going to write it with our vertical bars. So when I write a matrix with curved brackets or square brackets, it is the matrix itself. If I use straight lines to contour my matrix, that means I'm finding the determinant of this, of whatever's inside. So that is a difference to note, especially if you use multiple sources, or simply the question is given to you in this way in the future. So if they're giving a determinant for you to work with. So if I have A, B, C, D in curved brackets or box brackets, it's the same thing, but if I use straight lines, this means the determinant. Oops. This is the determinant. So I'm going to use that in this form, or this. I'm going to use that today. So we're going to go through and find the determinant of a 3x3 matrix here, and we are going to use some cofactor expansion. So notice we're going to find our column or row with the most zeros in it to reduce the work we have to do. So the determinant will be equal to this cofactor expansion along the first column, which I picked. So I have 2 times the cofactor at the position 2 is at, so it is in row 2, column 1. This is equal to 2 times -1 raised to the sum of the indices times the minor at row 2, column 1. So this exponent evaluates to an odd exponent, which will leave us with our negative sign. So we have -2 times the minor of what's left. So we are going to cross out everything in the row that 2 is in, and everything in the column was the first one I said, and the row. We're going to cross everything in the row that the 2 is in. So and then we're going to take the determinant of the rest of it. So the minor of 2, 1 is -3, 5, because that's what's here, and what's left, we have -3 and -2. So also now we have a good, nice 2x2 matrix we can work with, and as covered before, the determinant is equal to AD minus BC. The top left times the bottom right minus the top right times the bottom left. So this gives us -2 times, we have -3 times -2 minus -5 times -3. So what's inside the brackets is, we're trying to save some space here. So we have -6 minus 15, which is -21. If I -6 minus 15. Okay. So now we have a negative times a negative, so that means the determinant is 42 for original. Now is the tricky and tedious part. We are going to, so for each column in our original, we are going to sub these numbers in. So we're going to do that once, twice, 3 times. And then the rest of the numbers are going to stay the same in the matrix, but the numbers in that substitution will be gone. And then you're going to take the determinant of that remaining matrix. So let's go ahead and do that. So the determinant of A sub 1 is equal to the determinant. We're going to sub these 3 numbers in vector B into our matrix, our first column. So we have -2, -1, and +1. Then we're going to keep the same numbers of the rest of here. We're going to get rid of some of this stuff. Okay, so we have -3, -3, -3, -5, 0, and 2. So we can pick any row or any column when we do cofactor expansion. I'm going to go ahead and pick this column to perform my cofactor expansion. So the determinant of this matrix will be equal to -5 times the cofactor at row 1, column 3. This one is 0, so we don't need the second cofactor. Then we're going to add 2 times the cofactor at 3, 3. So that gives us -5 times -1 to the 4th, because 1 plus 3 is 4. We're going to add 2 times -1 to the 6th. So that will get rid of any sign changes. Oops, I think I forgot a step, sorry. So, and these are going to be each of these are going to be multiplied by the minor at that position. So this, since both of these are even exponents, due to the choice I made, there will be no sign changes when we multiply and when we add our minors. So, oops, sorry. So part of getting faster cofactor expansion is picking which line to cofactor, which column or row. So the minor at 1, 3, we are going to cross out the top row because it's all the stuff in that row or column that -5 is in. So we're going to ignore the first row and the last column, and we're going to take the determinant of what's left. So we have -5 times -1, -3, 1, -3, plus 2. This minor will be different as it's at row 3, column 3. So it will be at this position, and we're going to ignore everything else that shares a row or column with this number in the corner. So, and we're going to unignore what we used the first time. So we're going to take the determinant of what's left. So we have -2, -1, -3, and -3. So now we have a scalar times a matrix. So now we can multiply each number in the matrix by the outside number. So we have 5, -1, oops. Actually, it's -5. I said the wrong thing, but I wrote the right thing. So we have positive 15 here. And oh, that's not a matrix. We have to take the determinant. My apologies for that. So -5 times the determinant. So it's these two numbers multiplied together minus these two numbers multiplied together. So that gives us -3 times -1, which is 3. And we're going to subtract 3 times 1. So that's 0. Now we have 2 times the determinant here. We have -2 times -3, which is 6. And we're going to subtract 3 because we have 3 times 1. They're both negative, so that it becomes positive, but we're subtracting it. So then we have, so this evaluates to 2 times 3, which is 6. We're going to go back because I made a mistake with the first determinant here. So I apologize for that once again. So we'll see. So -1 times -3 gives us 3. So we have, sorry. And then we have a -3 times 1, and we're subtracting that, so that becomes this. So we have -5 times 6 plus 2 times 3. So we have -30 plus 6, which gives us -24. So that is the determinant of this matrix where we've subbed in our B vector as the first column. Alright, so now I'm going to make some room so I can work with the next two determinants we have to calculate. Alright, so after we just found that the determinant of the original was 42, and the determinant of the first one was -24, we are going to sub in our B vector into and replace the second column of our A matrix with the B vector. So the determinant of A sub 2, let's call it, is going to be the determinant of 0 to 0, gives you -1, 1, -5, 0, 2. Oops. So we're going to use some cofactor expansion again. To no one's surprise, we're going to use this one because it has the most zeros. So we have the determinant will be equal to 2 times the cofactor at 2 times the cofactor at row 2, column 1. 2 plus 1 will be a negative number. Actually, no, 2 plus 1 gives us an odd exponent, which will leave us with a negative result. So this term will end up switching signs to be a negative, and we're going to multiply by the minor at row 2, column 1. So we have, this is negative 2 times, we are going to scratch out everything in this that shares a row or a column with the 2. And then we're going to take the determinant of everything else. Sorry. We are going to take the determinant of everything else. So we have negative 2, negative 5, 1, and 2. So the determinant will be equal to AD minus BC. So the negative 2 times 2 is negative 4. Minus negative 5 times 1. So this gives us negative 2 times negative 4 plus 5, which is 1. So this will be negative 2. All right, let's keep on going with our third replacement and then our third determinant to go along with it. So the third one, so A sub 3 is equal to the determinant of matrix A, where we've subbed in vector B for in the place of our third column, which will have a 0, 2, 0, negative 3, negative 3, negative 3, and a negative 2, negative 1, and 1. So we're going to use the same column and perform the same cofactor expansion here. So we have negative 2. Actually, we have 2. Notice that we are in row 1, or row 2, column 1, rather. And those indices, add them together, we have 2 plus 1 is 3. So if we raise negative 1 to a power of 3, it remains a negative. So we're gonna end up multiplying our 2 by a negative 1. So that's why this is negative like before. And we're gonna take the minor again. So this one, similar process but a different minor, because, oops, what's left is gonna be a tiny bit different. Sorry, the device thought my pen was still on the screen. So we are going to ignore everything that shares a row or a column with the 2. So we're going to ignore the zeros like we already have, and we're going to ignore these numbers again, and we're going to take that the determinant of that new matrix there. So we have negative 3, negative 2, negative 3, and 1. So we have negative 2 times this new determinant. So we have negative 3 times 1, negative 3. We're going to subtract negative 2 times negative 3. Negative 2 times negative 3 evaluates to positive 6, and we're subtracting positive 6. So we have negative 2 times negative 9, which gives us a determinant of 18. So our third determinant is 18. So now we can use these determinants that we found to solve our equation after long last. So hopefully you've noticed why this isn't the ideal solution to solve for a linear system of linear equations, because obviously there's a lot of room for error. I made some mistakes probably. Well, hopefully I pointed them out, but there's lots of math to do, and to do the same thing that a row echelon form would do, and a lot harder. Or it's not as hard, but it's newer. So obviously these aren't your answers, but we're going to use these right now to find the answers. All right, so now we can use the determinants we painstakingly calculated to solve our system of linear equations. So now we have, let's turn the pen back on. So to solve for x, we will take the first new determinant and divide by the original determinant, which gives us negative 24 over 42. They are both divisible by 6. So we have 42 divided by 6 is 7, and 24 divided by 6 is 4, right? Sorry, my brain's kind of messy right now. So we can solve for y. We have the second new determinant, the second column, when we switch out the second column, divided by the original determinant. So we have negative 2 over 42. We can divide both these terms by both the numerator and the denominator by 2 to get negative 1 over 21. All right, and to solve for our third variable, we take our the determinant where we subbed in for our third column and divide by the determinant of the original. So we have 18 over 42. Once again, both the numerator and the denominator are divisible by 6. 42 divided by 6 gives us 7 once more. 18 divided by 6 is 3. So now our solution, the solution to our linear equation is negative 2, negative 1, 1. So the only time you would use this is if you were explicitly told to, and you would receive a mark of 0 if you did it another way, or you're given these determinants and then you can just divide these in this manner. Because obviously this was quick, but we actually had to do a lot of work to find these numbers. So hopefully this helps with your work. I wish you the best of luck and have a great day. Thanks for watching.